Hi everyone. This chapter we have finished talking about four methods. They are bisection method, regular Fossey method, secant method, and Newton's method. So let's do a comparison. So let's look at the inputs. Bisection method, we have an interval, right? So we have 2 points, A and B, f of A, f of B. And regular Fossey method, secant method, we also have 2 points, right? The 2 endpoints. So what does bisection method do? Let me use orange color. Okay, so bisection method, we have A and B, and we cut it into half. And then we decide which subinterval contains the 0, and then we continue and cut it into half. Okay, and the regular Fossey method, we also have the interval, and then we want to look at those 2 points, and we want to find the secant line connecting those 2 points, and then whatever the secant line intersects, the x-axis is our estimated 0. Okay, and the secant line is very similar to the regular Fossey method, but they are picking, so they are also the secant line passing through the 2 endpoints. But the problem is the points we pick the previous 2 points. Okay, where the regular Fossey method, we need to decide which interval contains the 0, and then we can continue. So this is the formula of the estimated 0. Okay, so this is the secant line passing through the 2 endpoints crosses the x-axis. Okay, and yes, so here, so xk plus 1 only depends on xk and xk minus 1. So we get a list of xi's. Okay, and so it depends on the previous 2 terms in the list. Okay, Newton's method, the input is only one number. Okay, and this is the formula. The idea is here. So we don't have a, so we have a point x0, and let's say our function look like this. We consider the tangent line. Okay, so the tangent line at that point cross the x-axis. Okay, that is Newton's method. So then we see bisection method and regular Fossey method. We need to decide which interval contains the 0 to continue. Okay, and the secant method and Newton's method, we don't need to do that. So does it bracket the 0? Yes. Yes. And then here, no. No. Is that okay, everybody? Because bisection method and regular Fossey method, we have to decide which interval contains the 0 to continue. So it brackets the 0. So that's why convergence is guaranteed, because it's bracketed 0 and the length of the interval is smaller. So we guarantee convergence. However, the secant method and the Newton's method, they don't bracket the 0, so we don't guarantee convergence. So we have the convergence theorem, and they're so similar. Okay, first we need f prime are continuous for all x in the neighborhood of the true value, right? Second, we need the derivative of the true value is not 0. And then the initial estimates x0 and x1 are sufficiently close to the true value. And here, because we only have 1 point, we need x0 is chosen sufficiently close to the true value. Okay, but they're kind of similar, the convergence theorem. Okay, now how about the order of convergence? So for the bisection method, we have the error bound for the kth iteration is b minus a over 2 to the power of k, right? Because each step we take half of the interval. Okay, we divide it into 2 equal subinterval. So that's why the length is half of the previous step. So far, so good, everybody. And for regular Fossey method, we have linear convergence. So the order of convergence p equals 1. And for secant method, the p is I think I have a typo here. This should be around 1.62 because it's actually square root of 5 plus 1 over 2. This is the actual number. So that number is approximately by 1.618033989. So around 1.62. Okay, and the Newton's method, P is 2, and we actually prove it using the Taylor series expansion. So far, so good, everybody. So that is the comparison among the 4 methods we have discussed. Okay, the next, I'm gonna talk about an iterative method. Okay, so Babylonian method. To find the square root of a positive number a, it is convenient to write the equation x squared equals a as the implicit equation x equals 1/2 times x plus a over x. How do we get that? Well, let's see. We can multiply it. Okay, so x equals multiply out, or maybe we should multiply by 2 on both sides. Then we have 2x equals x plus a over x. Both sides subtract x. We have x equals a over x. Both sides multiply by x. Then we have x squared equals a. See? We get back to this equation. So they are equivalent. Okay, so this provides the basis of iterative solution techniques by using the right-hand side of the equation to generate an updated estimate for the desired value of x. So you see the left-hand side is only x, right-hand side is a function of x. So that's why we can do x1 equals the right-hand side, we plug in x equals to x0, the previous term. And then the left hand side we call it x sub k plus 1. The right hand side we have 1/2, and then we plug in x equals xk. You see, we get an iterative formula. Okay, so we have xk plus 1 equals a function of xk. So far, so good, everybody? Okay, so definition. The number p is a fixed point of a given function g of x if p equals g of p. Geometrically, this corresponds to find the intersection of the line y equals x and the curve y equals g of x. So let me draw a picture here. So we have the line y equals x. Let's see. So this is y equals x, right? And we have the curve g of x. Well, let's say g of x like this, right? Okay. Let's see, like this. Okay, then this p is the fixed point because at this point p we have p equals g of p. So far so good. So furthermore, we can use the Newton's method to this function x squared minus a. Do you realize this guy? The 0 of this function is square root of a, which is the 0 of this equation. Okay, so when we use Newton's method apply to this function, then we can get the above formula. I give you as a homework exercise. But do you want to do it together? It's actually quite easy. So yes, I really hope that you can pause the video here and think about it. And if you're done, you can continue to play the video and let me tell you the answer. So we do f prime equals 2x, right? And then we just have xk plus 1 equals xk minus yk over yk prime. So xk minus yk is xk squared minus a. Yk prime is 2 times xk. So far, so good, everybody. And you can see we take the common denominator is 2xk. We get 2xk squared minus xk squared minus a. Plus a. Right? So we can see 2xk squared minus xk is xk squared plus a over 2xk. And this is the same as this guy, right? You can take xk as the common denominator, then you get xk squared plus a. So they match. So far, so good, everybody. Okay, example 8. Use 3 iterations of the Babylonian method to find square root of 7 with x0 equals 1. What is the absolute and percentage error of the third iterate? Okay, so let's see. To find square root of 7, well, i.e., we want to solve the equation x squared equals 7. So our a equals 7. So we just use the same formula, but we plug in a is 7. So far, so good, everybody. Okay, so this is the iterative formula. And then how do we type it into our calculator? So x0 equals 1. And then x1 equals, well, how do you type this in your calculator? We can do 0.5 and then we do answer plus 7 divided by answer close parentheses, right? And let's see what it is. Okay, let me clear it. So we do 1. And then we do 0.5 times answer plus 7 divided by answer in close parentheses. So far, so good, everybody. And we click enter. So x1 is 4. Right? How about x2? Well, let's continue. Right? We can do copy and paste. Paste here, enter 2.875. x3 is, oops, sorry, not this one. This one. 2.654891304. Okay, so 2.654891304. So far, so good, everybody. Okay, and then so this is a third iterate. Right? Actually, we can do more. Okay, let's see how many steps does it take this iterative scheme to stabilize. So we can do enter again. So 2.645767044. 2.6547. Oops, 645767 over 4. Oops, I dropped my pencil. 45767 over 4. Okay, and that is x4 and x5. Let's do more. let me close this first. Sometimes when I open too much browser or documents, my computer get freeze. So 2.645 751311. And let's see. Oh, you see we get the same answer now. So x6 is same. It's stabilized. So we can say this is the true value. And you can also test that out by, well, what's this guy? This is just square root of 7, right? And you see that's the same number. Okay. So it converges. Oh wow. This is so many digits, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 digits. Okay. In the 5 steps. So very good. Okay, and yeah, I would say this guy is approximately square root of 7. Now we want to find the absolute error and the percentage error. So absolute error equals the difference between the true value and our estimated. Okay, so this is our estimated 0 is this guy. So what I do is I usually use the bigger number minus the smaller number. One, 3, 1, 1. Okay, and what is that? Well, get our calculator and we can go up. Okay, we don't need to type it again. We can go up. So this is the number. And then minus this number. Okay, so we get 0.009139993. 9139993. So far so good, everybody. Okay, what is percentage error? Or relative error? Well, we're gonna use the absolute error divided by the estimated 0. The estimated 0 is 2.654891304. Okay, what is this guy? So we press enter and then use it to, oh, okay, so use that answer and divide it by, okay, I'm gonna copy this guy here and then enter. So 3.4426. Let's just do 0.003447. Okay, if I ask you, okay, this is approximate the true value to how many significant digits? Well, this guy is the same as 3.4427 times 10 to the 123, -3, right? And this guy is less than 5 times 10 to the -3. So we can say the estimated 0 approximate the true value to 3 significant digits. So far so good, everybody? Okay, so that is our example. Let's continue. Okay, so actually one equations we can find a lot of iterative formula for it. Okay, so and let's continue to look at this example. Find all real fixed points of the following functions algebraically. Okay, so we want to find fixed points. Fixed point means we want to find the x value such that x equals to f of x, right? So we have f of x equals to minus x squared. We set it equal to x. And then we can move all the terms on the right hand side. We get x squared plus x minus 2 equals 0, right? And then we can factor it. We have x plus 2 minus 1. So x is minus 2, x equals 1. So here we have 2 fixed points. So far, so good, everybody? Okay, and then next guy, we want to set it equal to x, right? That's the fixed point mean x equals f of x. So x is fixed point. Alright, and then we can both sides multiply by 2x. And this guy get 2x squared. Well, move all the terms to the right hand side. We get minus 7x plus 3. And let's put the equal 0 here. Then what happened? 2x, x. How do we get negative 7 in the middle? That's minus 3. We'll give a minus 6 and minus 1. Minus 6 minus 1 is minus 7. Okay, so x equals, this is 1 over 2. This is 3. So we also get 2 fixed points. So far, so good, everybody? Okay. Then we can also use intermediate value theorem to show a function g has at least a fixed point if it does. We can use mean value theorem to show a function has at most a fixed point if it does. Okay, so example 10 show there is a unique fixed point of the function f equals 1/2 cosine x. So far, so good, everybody? Okay. So, I would say the 0 step is, let me see. We can define, here, let's define h of x be the left hand side. Okay, so we want to find a fixed point. So we want to find x such that x equals f of x, right? So we can define h of x to be f of x minus x. Well, then this is the same as 1/2 cosine x minus x. And notice that x is a fixed point of f if and only if x is a 0 of h. Because if x is 0 of h, it means 1/2 cosine x minus x is 0, right? Oh, this is the same as saying x equals 1/2 cosine x. So x is a fixed point. So far, so good, everybody? Okay, don't get confused. So this is the first steps. Well then, to show there's a unique fixed point of f is the same as to show this h has exactly 1, 0. And we have done this before, right? So we need to show h of x has exactly 1, 0. Or 1 root, right? 1, 0 or 1 root. Okay. So we did this in the beginning of our class, right? We use the intermediate value theorem to show we have at least 1 root, right? And we need to check first, our function h is continuous. Oops. And it is because 1/2 cosine x is continuous everywhere. X is continuous. So that's why h is continuous. And then we also need to find a point. F of that point is positive. We need to find another point. F of that point is negative, right? So the easiest number we pick is 0. Then we have 1/2 cosine 0 minus 0. Cosine 0 is 1, so 1/2. That's positive. And then we want to find a negative number. Well, you can try 1. If 1 doesn't work, try minus 1, right? And here let's try 1. Then it's 1/2 cosine 1 minus 1. You know, cosine is between 1 and minus 1. So when you multiply by half, it's between minus half and half. Well, this guy, subtract 1, it must be negative, right? Okay, so we have find a point that's positive. We have find point is negative. So by intermediate value theorem, there exists a C such that h of C equals 0. So i.e. h has a root. Okay, and next step, we have to show at most one root. Okay, and we use mean value theorem. Well, first we want to compute the derivative. Well, the derivative of cosine is minus sine x. Derivative of x is minus 1. Okay, so sine is bounded between minus 1 and 1. Minus 1/2 times sine x is bounded between minus 1/2 and 1/2. Well, this guy subtract 1 is always negative. Is that okay, everybody? Yes. So then we can prove by contradiction. So suppose h has 2 roots and they're a, b. So it means h of a equals h of b equals 0. And then by mean value theorem, there is c such that derivative at c equals h of b minus h of a over b minus a. And then because the top h of b equals h of a, so that's why we get 0. And this is a contradiction to here. Oops, I should say h, right? Contradiction to h prime is always negative for all x. Because we have a contradiction, so whatever we assume is wrong, h cannot have 2 roots. So h has at most 1 root. And then therefore, combine step 1 and step 2, we get h has exactly 1 root. So f has exactly 1 fixed point. And that's finished our problem. So far so good, everybody. So if I give you another function and ask you to show there exists a unique fixed point, well, the steps are almost the same. So what do we want to change if we have new function? Well, you're gonna change this, right? And you might change a different point to plug in, but one point will be positive, one point will be negative. And then you do the same thing by intermediate value theorem. There is a c such that h of c is 0. And then second step, what is going to be different is your derivative is going to be different. And you have either always positive or always negative. Okay. And then also we prove by contradiction. Suppose it has 2 roots. And then in mean value theorem, there is a c such that x prime of c is 0. This is contradicting to the fact that our derivative, I just realized my derivative forgot to put the prime here. So it's good to check our work. You see, sometimes I make mistake as well. We're all humans, right? So we learn from our mistake, and don't be afraid of making mistake. I strongly recommend you to have a mistake book so you can collect all the mistakes you make in different courses together, and then right before the exams you can review this mistake book, kind of remind you don't make the same error again. It's very useful. Okay, and right, and all the rest are the same. We just say, oh, H has exactly one root, so F has exactly one fixed point. So far so good, everybody? Alright, let's continue. Okay, so for iterative techniques, it is important to know whether the method converges, i.e. whether the sequence of the approximated results approach to the true solution. It is very useful to be able to analyze algebraically whether a fixed point formula will converge, and if so, to estimate how rapidly. Okay, what's the order of convergence? What is the rate of convergence? The following theorem states conditions which guarantee that the equation x equals g of x has a fixed point in the interval from a to b. Then the iterative procedure xk equals g of xk minus 1 will converge to that fixed point. Okay, so this is the fixed point convergence theorem. If g of x maps ab to ab, okay, what does that mean? Well, let's say we have AB, right? And here we have AB. So it means G must lie in this rectangle, okay? So, or this is a square actually. So G must lie in this rectangle. It maps AB into AB. Okay, so you cannot exceed this square. Okay, it must be lined in. And then G prime is continuous on the interval AB. There is an n such that the absolute value of the G prime is less than this n. Okay, so what is G prime? Well, G prime is the slope of tangent line at x, right? For the points in the interval AB, right? Well, this guy means that the slope is less than equal to a fixed number for all x in the interval AB. Okay, once we satisfy those three conditions, then we have the conclusion. First, x equals g of x has exactly one solution. We call it x asterisk, so the true value in the interval AB. Okay, so this solution is the fixed point of G. Okay, so this guy is a fixed point of G. And then the fixed point formula iteration xk equals g of xk minus 1 converges to the fixed point for any starting estimates inside this interval. Furthermore, the error, okay, let error be the k estimate minus the true value, satisfies that absolute value of the error less than equal to n. Remember, n is the number which is the bounds for the slopes. Okay, so the k error less than equal to n times the k minus 1 error. Okay, so if you want to, then this guy is less than equal to n squared e k minus 2, right? So less than equal to n less than equal to n. Okay, let's see. Here, you want to have 0. 0 is like, E0 is like e to the k minus k, right? So n to the k. So this is n to the k times E0. i.e., we get linear convergence with asymptotic error constant n. So far, so good, everybody? Yes? Do you remember what is the order of convergence? So if we have this guy, lambda, and this guy to the p, p is the order of convergence, and lambda is the rate of convergence. Okay, so here p is 1, right? So we get linear convergence with asymptotic error constant, or we can also say rate of convergence, and it's greater or equal to the maximum of the slope of the tangent line, so the derivative g prime of x inside the interval. Okay, so that is the fixed point convergence theorem. So let's do some example. So for some convergence fixed point iterative scheme, xn plus 1 equals g of xn on 0, 1. We have x0 equals 2 and x1 equals 2 let's see. Okay, so let's make this problem more interesting, okay? So let me change this number to 2, 4. Okay, and this guy changed to 2, 4. Because 0 to 1 is just this, the difference is just 1. So when we calculate, we don't really see it there. Okay, so let's change the problem a little bit to make it more interesting. So far, so good, everybody? Let me use a different color. Which color do you like? Do you like purple? Okay. So, let's start. Okay, so on the interval 2, 4. So x0 is 2. Okay, so x0 is right here. Right? So, and suppose for all the x inside this interval, the absolute value of g prime of x is less than or equal to 1/4. So this is the bound of the slope. Okay, A, compute the error bound for x6. Okay, so now let's see here. Think about it. What is E0? What's the true value? So let's say the true value is somewhere here. What is E0? E0 is x0 minus the true value. Well, this guy is less than or equal to the length of this interval. Do you agree? Which is 4 minus 2, which is 2. Okay? And sometimes it's not necessarily the length of the interval. Think about it. If this is 2, this is 4. Let's say if my x0 is 3, then what is the E0? What's the distance between the true value? Well, the true value is at most 1. Can you see here? The true values is at most 1. The difference between x0 and the boundaries of the interval. So far, so good. So I would say in general, this guy is the maximum between the A minus A0 and B minus x0. The maximum of them. Okay, and in this case, that is 2. Alright, let's continue. Let me get back to my purple color. So, and furthermore, we know for all x inside this interval, and we have this guy less than or equal to 1/4. So this 1/4 is the n. we have, right? And then by the formula, we get E6 is less than or equal to, look at this formula. We're using this formula when k equals 6. So E6 is less than or equal to n to the 6 times the E0, right? And n is 1 over 4 to the 6. E0, absolute value of that is less than or equal to 2, right? This is less than or equal to 2. Well, this is 2 over 4 to the 6. Wow. This is, it's like, okay, you know, 4 to the 6 is like 2 squared to the 6. It's like 2 to the 12. And then 2 to the 12 and then 2 on top cancel, we get 2 to the 11. Right? And what is that number? Let's see. 1 divided by 2 to the 11. And, 4.88281 times 10 to the negative, what is that? 4. So far, so good, everybody. So this is the error bound for x6. Okay, so this is one direction. They give me the number of steps, right? The 6 steps, the 6 iteration. And then when you are looking for the error bound. Well, the second direction is we want to determine the minimum number of iterations needed to approximate the fixed point to within 10 to the minus 5. Okay, so here we're doing the opposite. We're finding the k is the number of iterations such that our error at ek, so it's less than or equal to n to the k E0. Okay, and what is that? Well, n is 1/4 to the k. E0 absolute value is 2. We want to have this error to be within 10 to the minus 5. Okay. Now what happened? Well, let's divide it by 2, right? Let's divide it by 2. Then we have 1 over 4 to the k less than or equal to 10 to the minus 5 over 2, right? And then we can do ln on both sides. So we have ln of 1 over 4 k less than or equal to ln of 10 to the minus 5 over 2. Oh, a lot of fractions. Okay, I'm going to simplify a little bit because I don't want to deal with a lot of fractions. Okay. So this guy is 2 over 4 to the k, right? So what do? I multiply by both sides. I multiply both sides by 4 to the k, and we also multiply both sides by 10 to the 5th. See, much nicer number, not a lot of fractions. So this is the same as 4 to the k greater or equal to 2 times 10 to the 5th. See, much nicer number than what we had. Well, we had like 1/4 and 10 to the minus 5 over 2. Wow, a lot of fractions. Even though we have calculator, but we need to type a lot of numbers in the calculator, a lot of buttons. So let's simplify it. We can apply ln now. So ln 4 to the k is greater or equal to ln of 2 times 10 to the 5th. And here we can bring the k down in front. So this is k ln of 4. And let's divide both sides by ln of 4. And you know what? Because ln of 4 is positive, so it won't change the inequality. So we still have greater than equal. And let's see what this number is. ln, where is ln? Oh, here. ln of 2 times 10 to the 5th and close parentheses, divided by ln of 4. Okay, so 8.8048. 8.8048. See, k greater equal, we want to find the minimum number for k, right? Greater equal, can you find an integer that's greater equal to 8.8? Oh, that must be 9. So far, so good, everybody. So sometimes students make a mistake because probably here student get a ln of a number that is smaller than 1, then ln of that number is gonna be negative. Well, when you divide by a negative number, it will change the inequality. Yeah, sometimes it might happen that. But think about it. In this problem, we're looking for the minimum k. So k must be greater equal to whatever answer here. Okay, and we pick the integer. So even though this answer, it could be 8.21, you don't round down, you must round up. Okay, because k need to be greater equal. Okay, so so now we have two directions. We can, given the number of the iterative steps, all right, and we can find the error bound, or we are given the error, we need to control the error within some number, and then we find the number, the minimum number of iteration needed. Okay, so far so good, everybody. Let's continue with the next video. All right, see you soon. Yeah, this is a long session. Bye.